This video covers Stat 454 Addendum, Principles of the Simplex Method. Before we discuss the technical aspects of the Simplex Method, I want to take some time to discuss with you why the Simplex Method actually works. What I have written down here is an LP from chapter 3.1 all the way back in the beginning of the semester. The LP asks us to maximize Z equal to 3x1 plus 2x2, subject to three constraints: 2x1 plus x2 less than 100, x1 plus x2 less than 80, x1 less than or equal to 40, and of course, as an LP, there are the sign restrictions. The sign of both variables is positive. So observation number one related to the principles of the simplex method: 3 and 2 are slopes of the objective function. Think back to what you know about slopes all the way from your college algebra days. The expression 3x1 could be thought of as representing as x1 increases by 1, z increases by 3. And the expression 2x2 could be thought of as x2 increases by 1, z increases by 2. So if the goal is to make z as large as possible, should I be increasing z by 3 or should I be increasing z by 2? The obvious answer is I should be increasing z by 3. I've just chosen x1 to be the important variable I want to analyze. In the context of the simplex method, this is going to get a special name. This is called the entering variable. So our goal now will be to increase x1, hoping that it increases z as much as possible. So the next obvious question is, how much can I increase x1 by? If I want to increase z, I should try to increase x1 as much as possible. In order to do that, I'm going to examine the three constraint equations. Let's pretend for just a second that x2 has no bearing on the situation. What's the most I can make x1 do if I ignore x2? Ignoring x2 gives me these three expressions. Let's do a little bit of a division right here to get x1 less than or equal to 50. So once I take the ratio of these right-hand sides and these coefficients, I see that x1 has to be less than or equal to 50, less than or equal to 80, and less than or equal to 40. There is a single number that satisfies all three of those inequalities. x1 needs to simultaneously be less than 50, less than 80, less than 40. That's the smallest value. x1 less than or equal to 40 is the most I can increase x1 by while satisfying all three constraints. So I'm going to increase x1 by 40. That makes this LP, once I increase x1 by 40, look like maximize z equal to 3 times 40 plus 2x2, subject to the constraints 2 times 40 plus x2 less than or equal to 100, 40 plus x2 less than or equal to 80, 40 less than or equal to 40, and x2 bigger than or equal to 0. Using all of these substitutions for x1 equals 40. Let me simplify this expression a little bit. Simplifying, I get maximize z equal to 120 plus 2x2, x2 less than or equal to 20, x2 less than or equal to 40, and x2 greater than or equal to 0. By applying all of these restrictions on x1 and simplifying the expression, I now have a simpler LP. Well, now I can take a look at the remaining slopes. The remaining slope is 2. So I want to increase z. I should increase x2. What's the most I can increase x2 by? So I'll do that. Let me not forget my subject twos. No more variables. I'm going to finish simplifying these expressions. The maximum value that comes out of this LP is z equals 160, and it occurs when x1 equals 40 and x2 equals 20. This basic idea of choosing the steepest slope and then finding the most that the associated x value can attain is the core idea of the simplex method. We're going to supplement this procedure with matrices and elementary row operations and the standard form of the LP in order to not have to do any guessing and make these simplifications much more mechanical. This covers all content related to solving the principles of the simplex method.